So you've learned all the rules for exponent laws. So if you can handle what we did on the review at the beginning of class, you're sitting in a pretty good spot for the test next week. You're probably at least developing a low proficient, depending on how well you do, what kind of mistakes you do. The last little bit, today's lesson, is going to be the most oddball lesson, probably the most difficult to follow because it's application kind of questions. So it's not one set of rules. You have to look at the questions, follow the pattern, figure out the pattern, and do it. So there's lots of different things, and you just gotta slowly take your time. That's why I did the review first. So we'll only do a little bit of our notes today, then we'll do a little bit of the notes next day, then we'll do the sum. Right? So today, we're not going to start on the first page. So we're talking about applications. One way exponents show up is with shape formulas. Right? And we'll talk about that next stage. And other ways that exponents show up are in these situations on the back page. So we're going to talk about those first. Right? Now, there's lots of things in math and science that has relationships. We have equations for it. This is, so looking at example 4, is an equation that you're going to use next year in science class. So, on a test, on a quiz, or on an assignment, I may give you an equation to use. I think there's so many different equations I can give you to use. Right? So there's no way to study for it. The only way you study for it is you learn how to use equations. Right? So that's what I'm going to talk about. So this equation that you're going to come across next year describes how projectiles work. Right? So when you throw something up in the air or a thing is falling, right? Projectiles always make an arc like this. It's by this formula. That's part of science 10 next year. Right? So I'm going to give you an equation. Your math teacher's going to give you an equation. Your science teacher's going to give you an equation. It's going to have numbers and letters in it. You need to figure out what do the letters stand for. So in the question somewhere, they'll describe what the letters are. Right? This might be a brand new equation, so you just read it. So here, the path of a skydiver falls according to this formula. So a skydiver would start at the top and kind of fall down like this. This is the formula for it. Then it goes on and says, hey, the letter D stands for distance. Maybe I'll write it on my formula. Distance. Right? And it's measured in meters. So all these are application kind of questions. They'll tell you if it's measured in feet or yards or kilometers. So it's measured in meters. Then it goes on to say, oh, the letter T stands for time. And it's measured in seconds. So this is time. Okay? So you need to read the question and figure out what each of the letters stand for. When I give questions like this on tests, this is like the #1 questions that students will leave blank. They just see the formula, they freeze, they blank, they leave it out. Honestly, it's probably one of the easiest questions on the test. Right? So to do these questions, you understand what the formula is, then you just got to use it. So it goes, hey, can you find the distance the skydiver falls after 2 seconds? Right? So step 1, write out the formula that they give you. 4.9 t squared. Next year, teacher will give you half a mark to 1 mark just for writing the formula. Step 2, use the formula. They gave you a number to put into this formula. Right? So they say, hey, put in the number 2 into this formula. But there's 2 different letters. There's a D and there's a T. Where does that 2 go? Does it go in for the D or does it go in for the T? T. Because it says it's 2 seconds. It's talking about time. So all you're going to do is you're going to replace the T with the number 2. And remember when we do this, we do it with brackets. So the T comes out. You stick the number 2 in. Everything else stays the same. All right? You got half the marks right there. Now all you got to do is calculate according to BedMath. And we've done lots of these calculations. There's some multiplication there. There's an exponent. What do we do first? Exponent. You got to do the exponent calculation. So you got to do this exponent calculation first. 2 exponent 2 is 4. We drop the 4.9 down. We have the little times. You multiply those two numbers. Grab a calculator, multiply those two numbers. 4.9 times 4. You got 19.6. Right? And you're almost at full marks. And all you have to do is give a little sentence, right? Describing what happened. You say, hey, the sky diver fell 19.6. Include the units. Is that centimeters? Is that feet? Is inches? What did it say in the question? What is distance measured in? Meters. So use the word meters in 2 seconds. That's it, right? It's probably the most common question to be left blank. Write out the formula, put the number in, and they're usually one of the easiest bed match questions to do. Right? That's it.
So 4 is double.
If it's 4, you can't just double it.
Wow.
Right? So I like that thought. If you double it, you would expect it to be just shy of 40. Right? Let's do it. So if we did the question 4, what did I do? The next one, instead of 2, we stick in the number 4 this time. All right? We do the exponent. 4 times 4 is 16. Then you have 4.9 times 16. Grab my calculator. 4.9 times 16 is 78.4. Not double. I like the way you thought, because you're thinking on patterns. So most of the stuff in grades kindergarten to grade 9 even, right, are called linear relationships. Right? So linear relationships means everything goes in a line, up or down. So twice the time, it's going to go double the distance, if it's linear. When you're talking about projectiles, it's not a linear motion. It's a curved motion. So that's why it doesn't go twice as far. It actually goes 4 times. It's actually a quadratic relationship here. And that's more into grade 10 and grade 11. That kind of idea, math-wise. You'll see this question in Science 10. You'll see questions like this, but that whole linear doubling thing, that'll be more of like a grade 11 question. All right. So of the application questions, I think this is probably going to be the easiest one for you. Right? The second easiest one is probably what we're going to talk about next day, is using shape formulas. That's just using a formula, plugging in. What makes those ones a little bit hard is you have to know some of the shape formulas. Right? That's what makes it a little bit harder, but it's very same similar thing to this. The hardest is probably question 6 and 5. Okay, these are just scenarios. You have to look at it, figure out a pattern. All right, so we'll do question 6 first, then we'll go over to the other one. Right? So question 6 goes, we have a bike lock. And it has 4 dials on it. So imagine a bike lock. It has 4 dials. I'll do a blue dial here, and a red dial, a green dial, and a purple dial. And they say, hey, the dials have numbers 0 through 9 on it. This can be anywhere between 0 and 9. That can be anywhere between 0 and 9, 0 and 9, 0 and 9. Now the question is, so you're buying a brand new lock and you're setting your combination. How many different combinations can this lock have? And you can probably do that question without any math knowledge. You can probably just reason it out. Can anybody guess how many numbers, how many combinations you can have for this? We'll work it out if you can. Close. Very close, George. You're off. That isn't quite right.
You could also have zero.
Huh?
You could also have zero.
But you can also have 0. So it's all the numbers between 0, 0, 0 and 9, 9, 9, 9. That's 10,000 numbers, right? 0, 0, 0, 1 to 999 will be 9,999 numbers, plus the extra 0 gives us 10,000 combinations. So we don't even need to do the math. We know the answer to this question. But you need to learn how to do that. Because I could change this question instead of saying, hey, dials 0 to 9, and say, hey, what if it was alphabet lock? It was A through Z. Then you couldn't do that question anymore. Right? Then it becomes harder. But the math still stays the same. So we're going to go through the math one because you got to know how to do all these different combinations. All right? So let's suppose instead of a 4-dial lock, let's make this scenario a little bit easier. If we go to the dollar store, we buy the cheapest lock we can. It only has 1 dial on it. Only has that blue dial on it. How many combinations can you have?
9.
Not 9.
10.
10. You can have 0, 1, 2, 3, all the way down to 9. It can have 10 different combinations. All right? That's not that secure. Somebody can easily break into it. You can guess 10 different combinations without too much time. So you okay? Maybe I'll spend a couple extra dollars at the dollar store and get it with 2 dials. Right? And if you have 2 dials, how many combinations can you have? 100. And how do we figure out? We want to figure out the schematic. So how do we do that? Well, if the first dial you set at 0, that means the second dial you can set any number between 0 and 9. Right? That's 10 combinations. If you set the first dial to 1, you can set the second dial any number between 0 and 9. That's another 10 different combinations. Right? So you can do that for every single one of these. So it would be 100 combinations. Why? For every 10 numbers on the first dial, we can have another 10 different combinations on the second one. So 10 times 10 is 100. Is that okay? All right. So using this logic, you go to Canadian Tire, you got a slightly better lock. What is the calculation if you have 3 dials? What would that calculation be? 1,000. But we go, for every single one of these, there's another 10. So it'd be 10 times 10 times 10. Right? So it'd be 10. The first dial 10. The second dial 10. The third dial 10, which is 1,000. All right? Okay. Or we can say this is 10 cubed. We can say this is 10 squared. Or we can say this is 10 to the exponent 1. Right? So if you have 4 dials, it will be 10 to the exponent 4, which would give us our 10,000 combinations. Okay. So let's go back to the alphabet lock scenario. So suppose the exact same situation, but we have an alphabet lock instead. How do we change our calculation? Right? We have 4 dials. The exponent 4 is going to stay the same. Right? The exponent 4 is going to stay the same. What does the base change to?
27.
26. Right? Because there's 26 letters in the alphabet. So that each dial has 26 possibilities. So if you had an alphabet lock, it would be 26 combinations, right? Times 4, because it would be 4, or exponent 4, right? So if you did our calculator and you did that calculation, you'll notice that it's a much bigger number. Instead of 10,000, an alphabet lock would have 456,976 combinations, right? So you need to be able to think that way. And if your teacher is being a little bit tricky next year, maybe they'll give you a lock question where one of the dials is numbers, the other one's alphabet. And you figure out how many combinations that is like that. Or some other combination like that. You need to be able to think both these ways. So this is really hard, right? So I'm going to show you different questions so you can sort of see how to come up with these patterns. And the more word questions you do, the more similarities you're going to start seeing. Right? Another very common question is population growth. So lots of things in life have exponential growth. One of those things is population. And this is how they predict how much bacteria is going to happen, how bad the flu season is going to be. They get a sample size, they know how quickly it grows, and they can make predictions of how bad the flu season is going to be, or how bad the COVID spread is going to be. It's all based off exponential growth, right? So here we have this bacteria. And this bacteria, the way it reproduces, it says it triples every 3 hours. So they have a colony of 50 bacteria to start with, and we have some questions. How many bacteria would there be after 3 hours? That's our first question, right? So we're going to do some simple calculations. Now, even if you can't remember what the formula for the patterns is, most of these questions you can use brute force calculations to figure out. Okay, so let's go like this. At the beginning, at the start, there are 50 of them, right? Then an hour passes by. After the first hour, how many bacteria would there be?
200.
Not 200. How does it reproduce? It sorry?
Triples by every hour.
It triples. So what's triple 50? 150. So you go, instead of just writing that number down, let's write down our calculation so we don't forget where the number came from. All right, so after 1 hour, we expect 150 bacteria to be there. Then another hour passes by. So we're at the 2-hour mark. How many bacteria do we expect there to be? 450, right? We take our previous population of 150 and we just triple it. Right? Then now we can almost answer a question. The 3 hours is not too bad. Right? How many would there be after 3 hours? What's our calculation we would do?
450 times 3.
450 times 3. Right? 450 times 3. You triple 450. Grab my calculator for that one. Times 3 is 1,350. So we can say after 3 hours, there'll be 1,350 bacteria. And you can do this with all the questions. You can do this brute force method. You can calculate all the numbers. Not too bad. Well, thank you so much. All right. But there is a problem with this method. Instead of after 3 hours, I could say after 10 hours or after 20 hours, how many bacteria there is. Then doing this method becomes very inefficient and probably lead to mistakes when tripling. So we need to be able to figure out a formula. So for the second question is how many bacteria there are after 5 hours. We're going to come up with a formula, right? And when you're coming up with formulas, you have to go back to the calculations and see the patterns, right? So our first calculation was 50 times 3, oops, I wanted red there, right, equals 150, right? Our second calculation was 150 times 3. Where did the 150 come from? Oh, the previous 50 times 3. So that was 50 times 3, that's our 150, and we tripled that. Oh, come on, tripled that, and we got 450. All right. Then our last calculation we did is we tripled 450. Oh, where did 450 come from? Came from this line here. So 450 came from 50 times 3 times 3. That's our 450. And we tripled it. And we got 1,350. So if I want to know how many bacteria are there after 5 hours, what do you notice? What would the calculation be? George?
Would it be 50 times, like, a repeated 3 for 5 times?
Yeah, if you look at this, for the first hour, it tripled once. We had 1 3. For the second hour, it tripled twice. So we have 2 3s. For the third hour, it tripled 3 times. So we have 3 3s. So for the fifth hour, we expect there to be 5 3s. And we're not going to write that out because that's a lot of 3s we're going to write out. So instead of doing it like that, we write it in exponential form. Right? And we could have done that at the earlier step, but our minds aren't used to thinking of exponential form. This first one, this last one could have been 50 times 3 cubed. The second one could have been 50 times 3 squared. The first one could have been 50 times 3 to the exponent 1. Right? We're not used to thinking that way. Right? So if we wanted to figure this out, it becomes a bedmass question, right? We do our exponents first. We're used to doing this calculation. We go 3 exponent 5. We get that number. We times it by 50. And it equals 12,150 after 5 hours. Okay. So that's how you create the generic formula. This is how all population growths happen. So if you know this structure, you can skip finding the pattern. So what you got to know is what do the numbers stand for, right? So this number here, this number 3, is how the bacteria reproduced, right? How the population reproduces, right? Because not all bacteria triple. Some of them might be doubling. Some of them might be quadrupling. So if I have a different question, say, hey, we have a bacteria that doubles every hour, that number wouldn't be a 3 anymore. It would be a 2, right? And this 50, where did that come from? This is our starting population. Right, we started off with 50 bacteria. It's like you do a whole different question. Oh, we start off with 200 bacteria, and it doubles every hour. And all you have to do is change those numbers if you know where they go, right? So this is the formula for population growth, and it's very similar to investment formulas as well, which you'll find out in grade 11. It's a good modification of this. Now, every once in a while, the question will say, hey, can you give me a formula for n? All they're asking you is come up with a generic formula, right? So the generic formula, we go like, hey, for this our bacteria, our population is equal to 50 times 3 to the exponent n, where whatever hour you want. If you want it 5 hours, you take the n out and you put 5 in. If you want 7 hours, take the n out and you put 7 in. That's all it's saying, right? So this is way different than everything we've been doing before. I just want to expose you to these different ideas. Like, don't worry about this too much on the test. At most, I'll give you 1 or 2 questions on day 5. Most of the test will be on days 1 through 4. But you do need to know this kind of stuff for next year. All right, that's